everyone, welcome to my presentation today. My name is Arananda UV and today we are going to break down precipitation method for biomolecule recovery in fermentation technology. We are going to explore how we pull valuable biopharmaceutical products out of a massive fermentation broth efficiently using basic principle of physical chemistry. Okay, let's start by placing precipitation where it belongs in the big picture of downstream processing, that is DSP. DSP is the entire chain of unit operations needed to capture, concentrate, isolate and purify our target biomolecule after fermentation. It follows a simple 5-step journey. The first one is harvesting the raw fermentation broth. The second is cell separation using centrifugation or filtration to get a clear liquid. The third step is precipitation for volume reduction and primary isolation. The fourth step is high resolution purification using chromatography. The fifth step is polishing, which includes final formulation and drying. So why do we need precipitation right at step 3? Imagine trying to run a 10,000 liter harvest straight through a high-cost chromatography column. It would drag your columns and destroy your budget. Precipitation acts as an economical primary concentration step. It strips away huge amount of water and bulk impurities early on, making it incredibly scalable for multi-thousand liter industrial harvest. Okay. Now before we jump into techniques, let me ask a simple question. Why do proteins stay dissolved in water in the first place? So, in a normal aqueous environment, non-covalent interaction between water and hydrophilic amino acids on the protein surface create a protective hydration shell around the molecule. So precipitation relies on two driving mechanisms to break the shell. The first one is hydration barrier removal. If we strip away the water shell, hidden non-polar patches on the protein surface get exposed. Second is chemical neutralization. When we eliminate electrostatic repulsion between molecules, short-range van der Waals forces, cohesive forces take over. The exposed hydrophobic patches stick together like Velcro, leading to a self-aggregation and phase separation. They fall right out of the solution. Okay, then our first major method uses neutral salt and it shows two opposite behaviors depending on salt concentration. First is salting in occurs at low salt concentration. Here salt ions gently shield surface charges, weakening the ionic attraction between individual protein molecules. This increases solvation and actually increases protein solubility. But as we keep adding salt, we transition into salting out at high salt concentration. Osmotropic salt ions compete aggressively for free bulk water molecules. They hog the water, stripping the hydration shells right off our target proteins. Driven by hydrophobic interactions, the protein aggregate. Mathematically, this behavior is governed by the Cohen equation. Log of S is equals to beta minus Ks into I, where S is the solubility and Ks is the salting out constant and I is ionic strength. Put simply, as ionic strength I goes up, protein solubility, that is S, drop exponentially. Ammonium sulfate is a global industrial favorite here because it's cheap, highly soluble, has great density properties and preserve native protein structure without denaturing them. Then the next is, in the next slide, our second major technique is isoelectric precipitation. Every protein has an isoelectric point, that is Pi, a specific pH where its total surface charge hits a net value of 0. If pH is higher or lower than the Pi, the protein carries a net negative or positive charge, causing a molecule to repel each other. At pH is equals to Pi, we reach a zero repulsion state. Without isoelectric repulsion to keep them apart, natural hydrophobic cohesive forces take over, leading to minimum protein solubility and rapid precipitation. The best part, It is completely reversible. Adjusting the pH away from the pI restores the net charge and dissolves the protein. A class industrial example is casein recovery, where acidifying bovine milk down to pH 4.6 triggers instant precipitation of commercial casein protein. Next up, we have organic solvent precipitation using miscible solvent like ethanol, acetone or isopropanol. How does this work? Adding an organic solvent lowers the solvent's dielectric constant. A lower dielectric constant amplifies the attractive coulombic force between opposite charges on nearby proteins, causing them to pull together. However, organic solvents carry a risk, unwanted protein denaturation. To prevent the irreversible folding, this operation must strictly run under cold conditions between -5 degrees Celsius and 0 degrees Celsius. The most famous industrial application of this classic Cohen process, which is used globally for human blood plasma fractionation. Okay. We also utilize polymer-based methods such as using non-ionic polymers like polyethylene glycol, that is PEG. PEG molecule take up physical room in the water, crowding the biomolecules into a smaller volume through steric exclusion until they aggregate. When comparing all these methods, sorting out is a low cost and high scalable, but requires downstream desalting like dialysis and ultrafiltration. Organic solvents offer moderate selectivity but carry denaturation risk and require explosion-proof equipment. And isoelectric precipitation is extremely low cost and easily scalable via simple pH adjustment. PEG offers gently recovery but can create high viscosity challenges downstream. To conclude, precipitation is an indispensable bridge in downstream processing, converting huge diluted fermentation broth into manageable concentrated products ready for fine chromatography. My talk today was built upon foundation bioprocess literature, including Stanbury, Whitaker and Hall's principles of fermentation technology, Paul and Doran's bioprocess engineering principles, and Harrison's et al.'s bioseparation science and engineering. Thank you so much for your time and attention. Thank you.